Have you ever stopped and just wondered how your phone does that? You take a few photos, sweep it across a landscape, and boom, a perfect panorama. It really does feel like magic, but it's not. It's actually this fascinating field called the geometry of vision. And today, we're going to pull back the curtain and see exactly how it all works.
I mean, really think about it for a second. Your phone pulls this off in, a couple of seconds? But behind that super simple action is this incredible dance of mathematics and algorithms. And this one problem, just stitching images together, is the perfect way for us to dive into the fundamental challenges and frankly, the really ingenious solutions that are at the very heart of computer vision.
So, at a high level, here's the game plan a computer follows. It's basically a 6-step process, right? From finding interesting points in the images all the way to blending them so you can't see the seams. Now, we're going to really focus in on step 4, the actual stitching, because that's where the geometric magic really happens. And to get that, we've got to go all the way back to the basics.
Okay, first question. How in the world do you model a camera with math? Well, like with any good engineering problem, you start simple. You strip it all the way down to its purest, simplest form, a totally light-proof box with one single tiny hole. This is what we call the idealized pinhole model, and it's going to be the foundation for everything else we talk about.
So, just imagine a point out there in the real world, say on a tree. Light is bouncing off of it in every direction. But only one of those light rays is going to travel in a perfectly straight line, pass through that tiny pinhole, and hit the image sensor on the back wall of our box. It paints one single pixel. See? It's just a pure, simple geometric projection. We're totally ignoring all the messy physics of lenses, for now.
Now, why is this so powerful? Well, because it gives us a mathematical blueprint for vision itself. We can now write an equation that predicts exactly where any point from the 3D world is going to land on our 2D image. This is the absolute first step, the essential piece you need to teach a machine how to see. And here's the formula that makes it happen. It might look a little technical, but it's just a fancy way of saying something you already know instinctively. Things that are farther away look smaller, right? The position of a point in your photo, it's just a simple ratio, a ratio between the camera's focal length, that's f, and the point's distance from the camera. It's so elegant, so simple, and it's the absolute key to how a camera translates the rich 3D world into flat 2D data.
But, of course, nothing in the real world is ever that perfect. This quote is a great reminder that the pinhole model, as beautiful as it is just a starting point. It's an approximation. Because, let's be honest, our cameras don't use tiny pinholes. They use lenses. And lenses, well, they bring a whole new set of problems to the party.
So yeah, that pinhole model is great in theory, but it has one massive practical flaw. It barely lets in any light, so you get a really dark, really grainy image. The fix? A lens. A lens can gather way more light, but as we're about to see, solving one problem introduces a completely different one.
And this right here is the fundamental trade-off. It's a classic engineering compromise. A pinhole gives you perfect, clean geometry, but a frankly terrible photo. A lens gives you a bright, sharp, beautiful photo, but it comes at a cost. It actually warps reality. It introduces distortion. And so our job as computer vision engineers is to find a way to get the best of both worlds by mathematically unwarping that image.
Now, the good news is that these imperfections aren't just random chaos. Nope, they are very predictable. And they fall into two main categories that we can actually model, and then we can reverse them.
Okay, so first up is what we call radial distortion. The easiest way to think about this is that the lens is kind of like a subtle funhouse mirror. Light that hits the edges of the glass gets bent more than the light hitting the center. This causes straight lines in the real world to bulge outwards like a barrel or get pinched inwards like a pinch cushion. Then you've got tangential distortion. That's a bit more subtle. It happens when the lens and the image sensor aren't perfectly parallel, which can make the image look just a little bit stretched or skewed.
And check this out. This shows you just how powerful modeling that distortion can be. On the left, that's the world as the camera's warped lens saw it. See how the door frame is all curved? But on the right, after we apply our mathematical correction, boom! Reality is restored, straight lines are straight again. Literally every high-precision vision application, from robotics to 3D scanning, has to do this exact step first.
So let's take a step back. We've seen that real-world cameras don't really play by the simple rules of the geometry we all learned back in high school. To deal with stuff like lens distortion, and especially perspective, we need a whole new mathematical language. We actually need a new way of thinking about space itself.
This quote just nails it. The geometry we're used to, Euclidean geometry, is built on these unbreakable rules like parallel lines never meet. But just think about a photo of train tracks, right? They look like they totally meet at the horizon, and in the image, they do. That's perspective projection for you. To model that, we need something way more powerful. We need projective geometry. Okay, this table shows us what's going on. Think of it like a ladder of geometries. Down at the bottom, you've got good old Euclidean, where everything's rigid. As we climb up, we start relaxing the rules. First, we allow things to scale up or down. Then we allow shearing and non-uniform scaling. And finally, at the very top, we get to projective geometry. This is the language of cameras. Here, almost everything we think of as fixed. Lengths, angles, even whether lines are parallel, can change. One of the only things that is preserved is a clever little thing called the cross ratio, which is a property that, amazingly, stays constant even when your perspective changes.
So, how do we actually work in this crazy, flexible system? Well, we use this absolutely brilliant mathematical trick called homogeneous coordinates. It sounds complicated, but here's the deal. By adding just one extra number to all of our coordinates, we can do something incredible. We can take all those messy, complicated perspective transformations and turn them into simple, clean matrix multiplications. It's a bit of mathematical wizardry, honestly, and it's what makes all of modern computer graphics and vision even possible. All right, let's bring this all back home. We started with a really practical problem, stitching a panorama. We dove into this perfect, idealized model. We smacked into the messy reality of lens distortion, and then we had to find a whole new mathematical language to describe it all. Now, let's connect all those dots back to making that panorama. So to stitch two images together, the computer is using projective geometry to find the one perfect transformation, the one perfect warp that makes them align. It really is like solving a puzzle. But instead of just sliding and rotating flat cardboard pieces, you're using the super powerful math to perfectly stretch and bend one image so that it lays seamlessly over the other, accounting for the unique camera perspective in each and every shot.
And why does this stuff matter so much? I mean, beyond just cool panoramas. Because these exact principles are the engine driving so much of the technology that's changing our world. This is how we build 3D models from a bunch of photos. It's how your phone's augmented reality can place a virtual sofa in your living room. It is absolutely critical for how a self-driving car perceives the depth and structure of the world all around it. It's everywhere.
You know, this whole journey has been about building the mathematical tools for a computer to see the world accurately, to get the geometry right. But that leaves us with one last really big question. Now that a machine can see, how do we teach it to understand what it's seeing? That is the next great frontier in this field, and maybe the problem that one of you is going to solve.